Hello everyone, I'm Aniket and I'll be presenting our work on thermal spread functions, physics-guided material classification. In this work, we propose a material classification framework that relies on thermal properties of the object. Our key observation is that the rate of heating and cooling of an object depends on the unique intrinsic properties of the material, namely the diffusivity and the emission or the absorption coefficient. We leverage this observation by gently heating the objects in the scene with a low power laser for a fixed duration and then turning it off while a thermal camera captures measurements during this process. We call this spatio-temporal distribution of temperature as thermal spread function, which is then used to solve an inverse heat equation using the finite differences approach, resulting in a spatially varying estimate of diffusivity and absorption coefficient. These tuples are then used to train a classifier that produces a fine-grained material label for each such region. Robust and non-destructive material classification is a challenging but crucial first step in numerous vision applications. Current practices include color and near-infrared based classification methods. These methods highly depend on color and appearance and require large labeled datasets to work correctly. More robust methods include spectral imaging, which allow only surface level detection of material, and invasive methods like haptic sensing, which use an artificial fingertip to get the thermal material properties. Thermal imaging methods enable contact-free estimation of thermal properties, thus allowing us to classify materials rapidly and in a non-destructive manner. As explained before, we observe the heating and cooling process using a long-wave infrared thermal camera, and the temperature transients obtained from this process are called as thermal spread functions. Here we show the TSFs on the left for microfiber and oak wood materials. We can observe that they exhibit different TSFs, which we then use to recover their thermal properties. Let's dive a bit into the heat equation. This is the partial differential equation for heat propagation in the presence of external heat source F. The term K denotes diffusivity and is multiplied by the Laplacian. Epsilon prime denotes the absorption coefficient. These two together serve as unique thermal identifier for materials. Here we show some values of readily available values of diffusivity and emissivity for some materials. This shows that these properties make the materials separable from each other. We saw earlier that this equation provides us an insight into the thermal properties of materials. But how can we use this equation to recover those properties? A naive image-based approach involves simple curve fitting to obtain K and epsilon prime values. In this, the time derivative is obtained from the temporal transients, whereas the Laplacian term is obtained from the thermal images. This approach often does not work as it incorrectly gives these non-uniformities for even uniform materials. We observe that a major reason for this is not accounting the diffusion in the depth dimension, particularly this term. Getting Laplacian in the depth dimension is not possible through simple observations, as we cannot see what's happening under the surface. Finite differences, on the other hand, is a well-known technique for solving PDEs such as heat equation. We develop a differentiable finite difference model that takes in initial surface temperature profile and has the thermal properties K and epsilon prime as the trainable parameters. Assuming some initial estimate, we perform the heat diffusion and compare the surface profiles with those captured from the camera, giving us the loss. We then backpropagate the loss and iteratively improve the K and epsilon prime estimates. So for given TSFs, we use the inverse FD algorithm and recover the thermal properties. We use these properties of materials as features for classification. We should also note that because of the low absorption and quick heat dissipation of thermal conductors, we are unable to recover their information using a low power laser, as their TSFs are almost flat. The recovered K and epsilon prime are used in this case to identify the material as brown tissue. On the left, we see a grid of materials we used for our classification. and the corresponding confusion matrix can be seen on the right. We obtain an overall accuracy of 86% over 16 classes. We tried few different classifiers with a varying number of input features and found the best performance with 50 features for an MLP with one hidden layer of 90 neurons. In conclusion, the main contributions of our work are observing the thermal spread functions and deriving initial temperature independent thermal factors to uniquely characterize a material. The use of finite differences method to solve the inverse heat problem for recovering parameters related to diffusion, absorption and emission, and non-invasively recovering these properties and using them to classify different materials. Thank you.